So yesterday we did arithmetic sequences, which adds or subtracts by a common difference. Today we're going to do geometric, which multiplies by a common ratio. There we go. So instead of subtracting to find that common difference, we're going to divide to find the common ratio. And I know looking at that, you're like, I can tell it's multiplying by 5. Everyone in here should be able to tell it multiplies by 5. But sometimes it gets a little bit complicated when you have decimals or fractions sitting in there. You can't really see it as easy. Okay? So the rule is take a term and divide by the previous term. That's going to give you your ratio. Easy enough? So, what is the common ratio of this bottom sequence? 3. And again, we can show the word for that even though we can do it in our heads. Okay? We all good? Clicking. To tell if it's geometric, arithmetic sequences are linear. You should be able to see a line, y equals mx plus b maybe. If they're geometric, they're going to be a very basic exponential function. So this is exponential. I can just tell looking at this it's geometric, but let's say we can't. The first term would be 3 over 2 to the first. The second term would be 9 over 4 because I'm squaring both of them. The third, I'm cubing both of them to the 4th power, and so on. So if I generate 4 or 5 terms, let's check to see if the ratios are consistent. Okay? So if I take the second term, divide it by the first term. Remember, when you divide fractions, you actually multiply by the reciprocal. That equals 3 over 2. That's nice. Let's take the 4th term and divide by the 3rd term. I should get the same. That can reduce to 3 over 2. So they're the same, therefore it's geometric. Easy enough? Let's do this next one. Just in your head, what's the first term? 1 minus 5 is negative 4. 1 minus 25 is 1 minus 125 is, and negative 624. Okay? Take a couple of them. So if I do negative 24 divided by negative 4, I get 6. If I do negative 624 divided by negative 124, I don't get 6. Uh-oh. So don't just assume. Okay? For it to be geometric, it's got to be just a base. So this is not geometric. The R's don't match. Okay? So when I say it's exponential, it has to be very basic. It has to be an A, a B with an exponent. That's exponential. When you add the 1 or do 1 minus that, it messes everything up. So it's got to be, an A times a B to the exponent. This one, the A is a 1. Okay? The exponent can be an N or an N minus 1 or N plus 2. It doesn't matter. But the exponent has to be where that variable is. Okay? All right. To write the geometric sequence, again, if I'm looking at this, what's my R value? 3, right? The sequences are very easy to write. You take the first term times the R value raised to the N minus 1. That's it. There's nothing you can do from that. Do not multiply 2 and 3 and get a 6. The 3 has an exponent attached, so it has to stay separate. But that literally is all you have to do to write the equation. First term times the ratio raised to the N minus 1 power. To write it recursively, if you remember recursive formulas, you have to have a first term given. So I'm going to say the first term is 2. And then for every term after that, you're going to write the ratio times the previous term. So remember, it's a subscript N minus 1 to show previous term. And that's it. So if I were describing this sequence to somebody, I'd say I'd start with a 2, and then you keep multiplying every term by 3. Multiply by 3, multiply by 3, multiply by 3. We good? All right. Find the first term, the ratio, and then write the sequence, the explicit form for that sequence. So the first term is 2. It's easy enough. The R value, the ratio, is the second term divided by the first. So if I multiply by that reciprocal, I get 6 over 10, which is 3 over 5. So the sequence is the first term times the ratio to the n minus 1. That's it. Very easy to write. Okay? But notice when you look at that, it's hard to see what the sequence ratio is. You got the fractions involved. All right, moving on. Find the 18th term of the geometric sequence whose first term is 7 and its common difference is 1.5. So try for a second, write your sequence down, and then you're trying to find the 18th term. So that's my sequence, yes? And all you're doing is plugging in an 18. They want to know what the value of the 18th term is. Okay? Easy enough? All right. Find in what position is the number 512 in that sequence. So when you're looking for the position, again, you need to write the sequence down. So the first term is 2. What's my ratio? 2 raised to the n minus 1. So that's my sequence. They're giving you 512. And you need to figure out what the n value is. So, what's the first thing you got to get rid of to solve for n? Divide by 2. You got to get rid of this front 2. Now, there are a couple ways you can do this. You can take the log of both sides, drop down to n minus 1, divide the logs, whatever. Or you can say, wait a minute, 256 is a power of 2. 256 is 2 to what power? Using your handy dandy calculators. It's 8, right? So we have the same base, therefore we can ignore the bases and set the equals, or the exponents equal. So your n equals 9. It's the 9th term. I need to see you do that with the formula. I do not want you to write that sequence out. Because guaranteed on the test we're going to try and make it like the 57th term or something, which would be ugly for you. Again, small number, you can find the power really quick. It's just as easy to take the log of both sides here. Divide the logs and then add 1. All right, that's sequences. Now we're going to do series. So a geometric series, again, we're adding up so many terms of a sequence. So when you have the summation of a geometric sequence, the formula we're just looking at this part. That's what you want to write down. The formula for the sum of n terms is a sub 1. Remember, that's the first term in the series. It may not be starting at the first term in the sequence. First term in the series times 1 minus the ratio raised to how many terms you are adding up, which is your n value, divided by 1 minus the ratio again. So that's what you want to write down for your sum. Good. Okay, so let's look at this example. You need to find your first term. So the first thing I'm going to do is I'm going to evaluate my sequence with whatever number you have here. So that equals 5. I mean, this is the first term. We have a perfect, nice little geometric sequence written. So that's the first term. And then you're going to find the sum. So it's the first term times 1 minus, what is the ratio? What's the R value here? 0.7. The ratio is that base. Raised to, how many terms do I have? From 1 to 15. 15. Don't let you confuse. You're going to subtract them and add 1. All over 1 minus 0.7. Now, it's not in the formula, but when you put this in your calculator, that denominator needs parentheses if you do it all at once. Or you just subtract in your head. Okay. You see that? You need to find your first term, then just apply the formula. So the second one, what am I going to plug in to find my first term? Five. This is the bottom, the index, lower bound. And I'm going to get some decimals here. I'm just going to leave with my calculator, and I'm going to start my next calculation with it. So we're going to take this big long number that we just put in times 1 minus the ratio, again, is that base, 1.2. How many terms do I have? From 5 to 26. 22. So the first term, again, you're going to take the sequence, and whatever this bottom number is, you're going to plug into it. Okay. All over 1 minus 1.2. Okay. Keep all those decimals. These are finite sequences. I want from this term to this term. Okay? This is for infinite series. I'm going to add this term all the way up till forever. Okay? And it's weird because you're like, how can you keep adding numbers and it's going to be an answer? Because we're good that way. That's the formula for the sum of infinite terms. Now, if it was an arithmetic sequence, I couldn't do this. Because in an arithmetic sequence, the terms keeps getting bigger and bigger and bigger and bigger. Their values. or bigger negative numbers, okay? So they never get small enough to add like this. If you have a exponential growth, again, it keeps getting bigger and bigger and bigger, never going to get small. But if your sequence represents an exponential decay, it's going to level off. It's going to approach 0. So the values are going to get so small, they're insignificant to the sum. Okay? So very easy formula. It's the first term over 1 minus r. And anytime you see this infinity symbol up top, that's when you're using this. Or if you see a sequence with a ... and they're telling you to find the sum. Okay? So we need to figure out our first term, which we have is 3, over 1 minus the ratio. Again, ratio, second term, divided by the first term, 3.4. That has to be a decimal. Between -1 and +1, it has to be a decimal value. Absolute value is between or is less than 1. Okay? It is possible to have a negative r if you have a sequence that's going from positive to negative, positive, negative, positive, negative. The r can be negative, but the absolute value of it has to be less than 1 to even use this formula. You get 5. So all those terms, ... included, will add up to 5. Okay. They're going to get so small it doesn't matter. And we are done.